All right, so as I have promised to my students today in differential equations, I'm going to talk about the application of growth and decay, right? So let me just share my, hang on, it should be here, present, share screen. Let me just share my screen to you so you can see what I'm going to discuss. So I will share the entire screen. So you can just ask question if you have some. All right. But I want the whole thingy. That's it. So here you go. Right. So this is our question. There's a problem. Um, Let me just get my phone and I'll check whether. Hang on. I'll check whether we are effective or not. I hope somebody is watching over there. I don't have my phone with me here. Okay, so this is a question. The population of a town is described by the function P of t equal to 300 times e raised to 0.03 t. So this is our function where the P of t represents the population after t years. All right. Okay. So first off is find the initial population. So if you have initial population, then it means that your P will be 0. Remember that our function is P of t equal to 3000 times e raised to 0.03 t. Okay, let's have a look again. Here is the function. P of t is equal to 3000 times 3 times e raised to 0.003 t. So initial population will be, let's put 0 to our t here. Okay, that's what that is what has been represented here. So P of 0 will be 3000 times e raised to 0.03 times 0. Why 0? Because initial population will be t equal to 0. Okay, there's no time lapse yet. So calculating this, you have 3000, which is this, times e to the 0. Why e to the 0? Because 0.03 times 0 is 0. Therefore, 3000 times, what is e to the 0? This is equal to 1. X to the 0 is equal to 1. 1 to the 0 is equal to 1. So any variable for that matter, or any number for that matter, when it is raised to 0 is always equal to 1. Okay? So e to the 0 will be 1. And 3000 times 1 is 3000. Therefore, the initial population of this is 3000. Okay? All right. Let me just clarify on the e to the 0 or x to the 0. Why is it equal to 1? So if you have, for example, x over x, yeah, we normally cancel that out and this is equal to 1. What's the reason? X over x. Because this is at the bottom. If you like to put it on top, it becomes x times x to the negative 1. wasn't it? Okay, so with the base x, this x here doesn't have any power. As you can see, it's not written, but the power is actually 1. So x to the 1 times x to the negative 1. We have the same base, so we do x, we just copy the base, and then exponent will be added 1 minus 1. So this will become x to the 0, or this is equal to 1. Why equal to 1? Because it came from here. X over x is equal to 1. And we can further explain that the derivation of x is x to the 0 is equal to 1 because of that concept. We are dividing a variable by itself, and that is 1. And by index laws, we can support it that x to the 0 is 1. Okay, let's move to the next one here. Number 2, determine the relative growth rate of the population. Determine the relative growth rate of the population. Right. Now, with the exponential growth formula here, exponential growth formula, it is actually PT is equal to PO times ERT, where your R is the relative growth rate, and we are looking for the relative growth rate here. Therefore, as you can see here, the 0.03 is R. So the answer will be the R equal to 0.03 will be multiplied by 100. So R is equal to 0.03, multiply that by 100. So 1, 2, you will have 3%. That is the relative growth rate. Rate is always in percentage. Okay. Why is it in percentage? Because normally rate is a fraction, and if you want to have it in decimal, like 1 over 3, for example, this is equal to 0.333. It's repeated. If you're going to multiply this by 100, then 1/3 is actually 33.33%. Okay. Therefore, the relative growth rate is 0.03. 0.03 times 100 gives you 3%. What's the answer here? It's 0.3 or 3%. What is the one accepted in the exam? Both. You can just say R is equal to 0.03. That's in decimal form. And if you want to change it to percent, then you can just multiply it by 100 to give you 3%. That's number 2. For number 3, find the population after 10 years. Okay, so we will be using the same growth rate or growth formula, and that's what we're going to use in here. So P, let's write it down. P of T is equal to P initial. No, it's not P initial, it's 3,000. 3,000 times E raised to 0.03 T. Let's have a look again. There. 3,000 times E raised to 0.03 T. Using this growth formula, then it says here to find the population after 10 years. Therefore, your T will be 10, right? So you have P of 10 is equal to 3,000 E raised to 0.03 times 10. That's it. Okay, so I will emphasize that by putting a green over it. So 3000 times e raised to 0.03 times 10, 0.03 times 10 means you're going to move one decimal to the right. Okay, so you will have 0.3. Your exponent, therefore, will just be 0.3 afterwards. And multiplying this is a calculator work. The P at 10 will be 3000 times e raised to 0.3. And you can do that with your calculator. And that will be e to the power of 0.3 will give you 1.349. And we know that e is a constant, which is 2.71 and so on. And multiplying 3000 with 1.349, you get 4047. This is already rounded to the whole number because we are talking about population. There's no such thing as 40.46.2, 40.46.7. So there's no 0.7%. So you have to round that up to the whole number. So the population, therefore, after 10 years will be approximately, that's why there's an approximation here, 40.47. You can either round it up or round it down. Okay, round it to the, and we know what's the rule for rounding numbers. When it's below 0.5 or 5, then we don't round it up, but you have to round it down. But if it's 5 and more, then you have to round it up. Okay, now we move on to number 4. Derive the differential equation that models the population growth. Okay, so this is the population growth formula or exponential growth formula. The exponential growth formula, okay. Pt is equal to P initial times ER to the T. PO or P initial times E raised to RT with respect to time to find the rate of change of P with respect to T or dP over dt. Well, anyway, so next is we're going to differentiate our formula. So differentiate P of T and then differentiate as well the one at the right side. So using chain rule would be, because there are two items in here, there's no problem with P of T because this becomes dP over dt. This is the same as your V is equal to pi r squared over h and then h dh over dt and dV over dt, something like that. Now PO here will just be out of the d over dt or out of the derivative equation. Why? Because PO is at first will be 0, isn't it? Okay, and then you have to get the derivative of e raised to rt. Now, we know that the derivative of EU will be equal to the derivative of u with respect to dx and EU, e to the u times du over dx. All right. So here, our EU, our EU is e to the RT. Our u is RT. Our du will just be simply R. Why? Because T is 1. All right. So dP over dt, therefore, will be equal to PO, and then if we will rewrite this one, it will be R times ER to the t. Okay, that's the coefficient of your t. All right. And then PO times R times ERT, that will be the derivative of e to the RT. So therefore you have P of t is equal to PO e to the RT, but your PO e to the RT is actually your PT. So going back here, PO e to the RT will be substituted by PT. So dP over dt is equal to R, which is this, and then POERT will be your PT. Okay? If we remove that one now, then you have dP over dt is equal to R. PO e to the RT is your PT, which is equal to PO e to the RT. So this is now the derivative of the exponential growth formula. Using this derivative, and number 5 is solving the differential equation to find the population at t is equal to 15 years, we can now use what we have derived. So what we have derived here, let me just get it again. dP over dt is equal to RPT. That's number 5. dP over dt is equal to P times PT RPT. What happened there? Times R. Or simply dP over dt is equal to R times PT. Okay. Now, what is R? R is 0.03. We have determined that earlier on. So, our working equation for number 5 will be dP over dt equal to 0.03 times dt. Okay. Now, to find the population at t is equal to 15, then we have to get an initial value of p, which is p at 0, and that is 3,000. Because this is in terms of dt, then we have to do an integration. Also, we have to position our variables properly. Why? Because your p must go here and your dt must go there. So you have dP over P is equal to R P of T dt. Can you see that? All right. But what is R? R is 0.03. Okay. So dP over P will be equal to 0.03, which is R dt, but we have P at 0 will be 3,000. Okay, but let's just take the awayment time and do the integration. We integrate this and we integrate that. So integrating dp over p, the integral of 0.03 times dt, then because the derivative of p is dp, then it results to ln p. And when you're going to integrate 0.03 times dt, then you will get 0.03t. The integral of dt is t plus c. Now, we need to find for c. When p is equal to 0, then it's equal to 3,000. We dealt with that earlier on. So, ln, let's get back here, ln of p. If p is 3,000, ln 3,000 is equal to c. Okay? Substituting the c equal to ln 3,000 here, then you will have ln p is equal to 0.03t plus ln 3,000. Now, because both are ln, we have to convert this one into natural logarithm as well. And because this is a plus, so plus means multiplication. Hence, we do ln of p is equal to 3,000 times e raised to 0.03 t. You're going to raise this as a, or you're going to convert it as a power, because ln p will be equal to e to the 0.03t ln 3,000. Why is it that it's e? Look, for you to make this one a part of the natural logarithm, then it must be converted to a natural logarithm. Okay. And if the conversion is e to the power 0.03t, if you change that to a normal number, then this power becomes the coefficient of ln e, 0.03t ln e. And if you cancel that, because ln e is equal to 1, then it goes back to the normal 0.03t. Okay? Now, we cannot combine a normal number or a normal variable with natural logarithms if you're not going to introduce e as a base. Right, having this one now, ln p is equal to e raised to 0.03t plus ln 3,000. Then, what are we going to do next? We will substitute the value of 15 because we are looking for the population after 15 years. Okay, so we have p to the t, or p of t. But why is it that became p of t? Both are already ln, so we can remove that. Okay, and make them both a normal number. You can only do that if you have changed the normal to an e notation or exponential notations. So now we can just remove the ln. Okay, remove the ln. Now, p here will be in terms of t. That's why it's p of t. 3000 times e raised to 0.03t. And because it's a function of t, you can substitute this t here with 15. So p of 15 will be 3000 e 0.03 times 15. This is a calculator work again. So putting this one in your calculator, you have 3000 times 4.481. This is the equivalent of e raised to 0.03 times 15. Then you will get a rounded value nearest to the whole number, that is 13,443. It could be 13,442.1, point 2, point 3, point 4, but it's not 13,442.5, point 6, point 7, point 8, point 9. If that's the case, then it will be rounded up to 13,443. So to end it, the population at 15 years, or the population in 15 years, will be approximately 13,443. Okay, so we have answered 5 questions, and this is the scope of the final. Hang on. That is the scope of the final test when it comes to growth and decay, right? I will also be presenting another topic on Newton's cooling system. And this is about Newton's cooling time, I should say. Okay. All right. So this is all for now, and yeah, I'll see you in a bit because I have still to prepare for my materials. Bye for now. And if you have some questions, just write in the box below, and yes, I'm gonna answer them. Thank you, and bye bye.